the change of variables in double integration. Now suppose you were calculating, you had the system in the x, y coordinates, that means the Cartesian coordinates, and now you have to move somehow into another system, say u and v. These u and v, they could be anything, they could be theta r, right? They could be anything other, that means they could be polar coordinates, they could be cylindrical coordinates or curvilinear coordinates or anything. These are the Cartesian coordinates. Now say you wanted to shift from this system to this system, because now say your geometry or the area that you wanted to calculate is typical and could not be solved here, right? So you are going to this particular system so that you could very easily and by reducing the computations solve this whatever you wanted to calculate, right? So for that, suppose in the Cartesian coordinate you have already calculated what is the area or what is the double integral of the given function f of x, y, dx, dy. So this double integral in this system would be equivalent to this integration, double integration over this region B, where the function would now be instead of x. So suppose we are having this relationship that x is given to be some function of the variables u and v, and y is also given to be some another function of the variables u and v. So in this case, instead of this x, I can write phi of u comma v, and instead of this y, I can write psi of u comma v. Now, and here du and dv. So what you have done, you have shifted this to the system, but there is one flaw here. The flaw is that in shifting from here to here, you have missed out something that is given by the Jacobian. If you remember, what was Jacobian? Jacobian gives the relationship when you shift from one system to another. So here you have to write down the value of the positive value of Jacobian, right? And if you remember the formula for Jacobian, what is this Jacobian? This Jacobian J that represents the change in the variables x and y with respect to the change in variables u and v, and it is calculated by the determinant by taking the partial derivative of x with respect to u and partial derivative of x with respect to v, and then by taking the partial derivative of y with respect to u and by taking the partial derivative of y with respect to v. So whatever is this value, moreover this should not be equal to 0 for any value. So in that case, you can substitute this value here and this integral is equivalent to this particular integral. So this is how you change from one system to another. Okay. Now I'm taking the special case where instead of the variables u and v, I am taking the polar coordinates. So if I am taking the polar coordinates here, so I very well know what is the relationship between the Cartesian and polar coordinate, that is x is equal to r cos theta and y is equal to r sin theta, because this is how you write down the variables, right? So I can show them to you also. Suppose this is some point x comma y in the Cartesian plane, and if you know what is this r, this distance is r, this angle is theta. So from here to here, what is the distance? This distance is x, and if you use the trigonometry, you complete this triangle, and because this is 90 degrees, so this is also equivalent to r cos theta. So your x is equal to r cos theta, and similarly this line is equivalent to r sin theta using trigonometry. And what is this distance? This distance is equivalent to this distance, and actually this is y and this is r sin theta. So that is how you obtain these values. Okay. So in this case you have x, the relationship between x, y and r theta. That means you are now moving from xy system to r theta system. So in this case, what is the Jacobian? The Jacobian would be given by the relation del x by del r, del x by del theta, and then del y by del r, del y by del theta. So now we can compute these quantities. So the derivative of x with respect, partially with respect to r, keeping theta constant, would be cos theta, and it would be minus sin theta. And when you take the derivative of this partially with respect to r, so that means you will keep theta constant. So this quantity would be sin theta, and this quantity would be r cos theta with a with no negative sign, right? R would be as such, and then the derivative of sin theta would be cos theta. So when you solve this, you will have here also you will have r, right? Yes, because when you take the partial derivative of x with respect to theta, r would come as such, and then the derivative of cos theta would be minus sin theta. Yes. So now when you take the determinant, you multiply this term with this term, you have r into cos square theta, and then minus of minus r into sin square theta. So basically this becomes equal to r into cos square theta plus sin square theta, that is equal to r. So this is your Jacobian. So in this case, your formula for double integral simply reduces to the double integration over the region A of the function f of xy dx dy, that reduces to the double integration over the region A of the function, instead of x now we will be writing r cos theta, instead of y we will be writing r sin theta, into the value of Jacobian that we have just calculated, equal to r into d theta dr. Now it could be anything, dr into d theta. So this is the relationship when you are shifting from the Cartesian system to the corresponding polar system, right, or the polar coordinates. So here usually the main part here is how can you take the limits here. So before going on to there, let us see one question, or let me first tell you how can you take the limits here. So it is a general rule that it is more easier when you take the limits of theta first and the r. That means you take the variable limits of r and the constant limits for theta, right? And whatever is your function you write here, and so that means dr and d theta. So this is a good practice. In this way your calculation becomes easy, right? And how do you take the limits? Suppose we are talking about this particular circle having equation x square plus y square is equal to 1. So in this case, what is your r? R is equal to 1, because the radius here is equal to 1. At any point, if you take any point, the radius is going to be 1, and the angle here, that varies from 0 to 2 pi, right? So your theta varies from 0 to 2 pi. So suppose if you wanted to calculate what is the variable limits for r in this particular case, that would simply be equal to, because r is moving from here to here, and suppose you wanted to calculate the area of this particular area. So in this case, this thing is equal to r varying from 0 to the value of r here, that is equal to 1. Here the limits are constant obviously, but in other cases the limits could vary, and theta varies from 0 to 2 pi. So if you notice, the limits of theta will always be constant, but sometimes the limits of r can be variable limits in terms of defined in terms of theta. So let us discuss